Hi, this is Dr. John Bergdorf. In this video, we're going to look at compound interest, which actually turns out to be a very practical application in everyday life of exponential functions. Now, you may know a little bit about compound interest already. Let's change cameras here real quickly, and I want to show you a basic definition. So the big idea of compound interest is that the interest you earn on an account is reinvested into the account periodically, and that is referred to as compounding. And the purpose of that is that you can earn interest on your interest. So compounding, for example, might be done monthly. The interest for a month is calculated. That interest that's earned is put back into your account. The next month you earn not only on your initial contribution, but also on the interest from the first month. The formula for that is fairly straightforward. Notice that it is exponential in form. Let me define what some of these quantities are. P is the principal. That's the amount that you originally invest. R is the annual interest rate, which, by the way, needs to be stated as a percent, as a decimal rather than a percent. It's usually given to you as a percent. You have to restate it as a decimal. N is the number of compounding periods per year. So, for example, if the interest is compounded monthly, there's 12 months in a year, so N would be 12. T is time, that's given in years. And A represents the amount that you have after that many years. And again, this is what the formula looks like when all is said and done. Let's do an example immediately so we can see exactly how this works. Keep the formula visible there for just a minute, as long as we can anyway. So suppose $3,000 is invested at 5.4% annual interest, compounded quarterly for 10 years. How much will you have? Let's see if we can identify what values we have and what we're trying to find. So the P is the principal. That's the amount you originally invest. And that's given right here. The P is going to be $3,000. The R is the annual interest rate. Now notice that is given as a percent. So you have to change that to a decimal, 0.054, moving the decimal 2 places to the left. The N is the number of compounding periods per year. This is sometimes something you have to look for a little bit more. Notice that this interest is going to be compounded quarterly. That means 4 times a year, so N is 4. And finally, T is the number of years, and that's going to be 10. Now, what you're trying to find is the amount in 10 years. That's going to be your A. So A is the quantity that you don't know. And we'll plug all of this into my formula up here. So the A will be equal to P is 3,000 times, in parentheses, 1 plus R, that's my 0.054, over N is quarterly, so that's 4, raised to the N times T, that would be 4 for N, and T times 10. T is 10, so 4 times 10. That's the calculation that we need to do. Now, let's let the calculator do all the work for us. So I'm going to switch over to a calculator and see what that looks like. I need to switch cameras, and then I need to share the screen like this, get that out of the way, and get myself out of the way as well. So I've repeated over here exactly the calculation that I had written by hand, and we're going to show how to do this on the calculator. Basically, you enter it exactly the way it looks. So you enter the 3,000 like that. Then you have to open a parentheses and 1 plus 0.054 divided by 4, close the parentheses. To raise something to an exponent, you use this caret key here. It looks like a little hat. And the one thing that's not immediately obvious, if you have one of the older calculators, this will not look like it's up in an exponent. And in those cases especially, you have to make sure you include everything that's in the exponent in parentheses. The newer models, you don't really have to do that, but just to sort of make a good practice out of it, I'm going to keep everything that I need to calculate in my exponent inside parentheses. So the 4 times 10 in parentheses. And then this is exactly on the right, the calculation that I'm asking for on the left. And we hit enter. And this is the number that we get. Now, when I write my answer down, I need to remember 2 things. First of all, this is an amount of money. And like every word problem, there's often a need to express your answer with some sort of units. Because we're talking about money, we want to make sure to indicate that we've got dollars. And again, because we're talking about money, it makes sense to round everything off to the nearest cent. So round to the nearest cent, this would be $5,129.46, rounded off. Okay, that's a good example. Let's do a different one that's involves something else. So meeting, we're going to switch the camera again. Now, this formula can be used for various kinds of compounding. The compounding periods might change. Typically, they are either monthly, which is n is 12, or quarterly, which is n equals 4. Every once in a while, you'll see that be daily, and there's an interesting tradition that when you're compounding daily, n is 360, not 365. But there is also a concept of being able to compound interest continuously, continuous compound interest. Let me get the whole thing on the screen there. There we go. Now, the idea of this might sound physically impossible, but in theory it is. Rather than compounding once a month or once a day or once a second, we compound the interest every micromillisecond, like this, just every micromillisecond. You can model that actually using calculus to derive the equation, but you can model that with an exponential function that looks more like the types of functions we use for exponential growth and decay. In this, the P still stands for the principal, the R still stands for the interest rate, T still stands for time in years, the E is the familiar number 2.718, and it might make sense that if you compound everything instantaneously, continuously like that, that you maybe should end up with a little bit more money. Let's see how that works. So let's suppose that $3,000 is invested at 5.4% annual interest, compounded continuously for 10 years. How much will you have after that 10 years? So let's see what we're given. 3,000 is going to be my principal, so P is 3,000. The R is the interest rate. Again, you have to convert that to a decimal, 0.054. T is time, and that's going to be 10. And the A is what you're hunting for. So we would have A equal 3,000 E to the 0.054 times 10. Now again, we're going to have our calculator do the work for us once we see where everything gets plugged in. So let me go back over to my calculator view. Give me a second here to switch the camera back and then share my screen. And let's look at the next calculation. I'm going to slide that down. Here's the exact calculation that we wanted to do. 3,000 e to the 0.054 times 10. Entering this into the calculator is easy too. 3,000. And then to get the e to the x, that is a second function feature on the natural log button. So you have to hit second function, followed by the log button, which will give you the e to the exponent. Again, quantities and exponents, it's best to keep those in parentheses, and then it would be 0.054 times 10, close the parentheses, and the answer is this. Writing my answer with the proper units, that would be $5,148.02. Now, since the other calculation is still on the screen here, this $5,129.46, that represented quarterly compounding. This represents instantaneous compounding, and you can see you've gotten a little bit more money from doing that. Now, once you know these two formulas, there's a bunch of other questions that you can answer, and I'm going to show you one that I think is a meaningful one. So I'm going to switch cameras again and show you a different example that asks for something that's a little bit different. So the question here, get this all straight, takes a second. You invest $1,000 at 4.81% annual interest, compounded continuously. So we'll use this formula for compounding continuously. How many years will it take for your investment to grow to $1,781? Now the same formula applies, but let's see what we've been given. The $1,000 is the amount you invest. So that's your principal. This is the interest rate. Again, we have to convert it to a decimal. That would be 0.0481. How many years will it take? That would be an interest of time, or a value of time. And we don't know what that is. We're going to have to solve for that. And then the investment grows to $1,781. That would represent that amount that you get after a certain number of years. That's your A. So plugging everything into the equation, you would this time have 1,781 equals 1,000 e to the 0.0481 t. And I need to solve for t. I need to get the t by itself. So let's talk about how to do that. Well, it would be easiest if we could get the exponential factor by itself first. So I'm going to say, as a good first step, let's divide both sides by 1,000. Now, the calculation on the left is simple. It's just moving a decimal, but I'm going to leave it be because it might be more complicated in other settings. And I want to show you that the calculator will do everything for us. Whoops, sorry about that. The 1,000s will divide out. And then I'll have the exponential expression by itself, 1781 over 1,000 equals e to the 0.0481 t. And like we've seen before, if your task is to liberate a variable out of the exponent, the best way to do that is to take a logarithm of both sides. Since my base is e this time, a natural logarithm makes sense. And then using that inverse relationship we've seen before, that if you have the logarithm base a of the same a raised to some power, you just get the power, again, because those are inverse functions. Then the quantity on the right, well, let's copy the quantity on the left so we don't lose it. The quantity on the left will simply be the exponent, the 0.0481 t. And that's going to make it possible, very easy, to solve for t. Now, let's divide both sides by 0.0481. And just rewrite that. We see that the 0.0481 will divide out on the right. And I'm going to put the t on the left just because that's more familiar. T is equal to the natural log. Let's put parentheses around this. It'll just make it easier not to get lost in the calculations. Parentheses around that fraction, and then 0.0481. And our calculator can handle this for us all at one time. We don't need to do little bits and write them down and other little bits and write them down. Let's take a look. So I'm going to switch cameras again and share the screen again so I can show you my calculator. Over here on the left, I've written down the calculation that we just figured out that we need to do, just so it's handy. And let's do this on our calculator. So the numerator only contains one factor. We don't really need to keep parentheses around the numerator. We will need to say natural logarithm and then have parentheses around the quantity inside the natural logarithm. 1781 divided by 0.0481, just copying that down. Oops, nope, got the wrong thing, so sorry. Let me back that up. I looked in the wrong place, that's not right at all. The number down here in the denominator is 1,000, 1,000, close parentheses, sorry about that. Now that looks right, that's the numerator. Divide all of that by the 0.0481, that does come in sooner or later. And now the calculation I have on my screen exactly matches the calculation I've got written down over here. Let's hit enter and see what we get. 11.9994834. You know what? I believe that is pretty darn close to a 12. Remember the T stands for time, and as a word problem, I want to make sure that I include units. Time is in years, so the amount of time it would take would be 12 years. All right, that's a little bit about compound interest, including continuous compound interest. It's a great example of using exponential functions.